Hello students, welcome to EPG Pathsala. I am Professor D. Velmurugan from Center for Advanced Study in Crystallography and Biophysics, University of Madras, Gindi Campus, Chennai 25, and I was formerly the head of the department. Now I am working there as the University Grants Commission Basic Scientific Research faculty. Today I am going to teach you a module dealing with protein structure determination methods from the paper Biocrystallography. So, students, let us see what I am going to teach you in this model. You are going to learn, after getting an introduction from me, about the molecular replacement method which was in existence in the beginning of protein crystallography. Then came the single isomorphous replacement and also multiple isomorphous replacement, about which you will be discussing. Then another important technique known as anomalous scattering is also there for macromolecular crystallography and also in small molecular crystallography. That also will be taught. First problem, as you know, is the bottleneck in X-ray crystallography, not only in small molecules but also in macromolecular such a determination. By phase problem we mean the missing information of the phase values of Bragg reflections from diffraction experiments, which are required, along with the experimentally measured Bragg intensities, from which of course you can take square root and get the structure factor amplitudes. These two are needed to do the Fourier synthesis, which is nothing but the calculation of electron density to locate the electron density maxima, which is nothing but the atomic sites. The idea conceived in 1970s was use the coordinate of a homologous structure to solve the structure of an unknown protein. That is known as molecular replacement. You are replacing this molecule by another for which structure is known. So don't ask me how that structure was solved. So only limited cases this was applicable those days. The molecule in the unknown unit cell is replaced by a homologous molecule. The homology means at least 20 to 25% homology is there. No? Then you can use the known structure as a model to get the new structure in the unknown unit cell. When I say unknown unit cell, don't get confused, because we don't know what are the unit cell contents. We don't know the molecule inside this unit cell, even though we have the X-ray data collected for this. For this as a model, you use some other molecule for which a structure is available, and this molecule should be homologous to the unknown molecule at least to 20%. So if it is already known, then you use that, and this technology is known as molecular replacement method, or abbreviated as MR. But as I told you, if you don't have a homology of at least 25%, then we cannot use this method. That is why before 1970, if you look into the deposition of protein structures, no, we can just name the proteins that are less than 20 only there that time. Now we do every week we have a deposition of minimum 125 to 150, which is possible, of course, due to the technological development or molecular biology techniques being developed, and with the synchrotron source high energy radiation developed and robotic crystallization, whatever may be the thing. Main technique is the multi-wavelength anomalous scattering and single wavelength anomalous diffraction experiments, which are possible in the synchrotron source. And this simplified the tedious job of preparing the heavy atom derivatives in those days. So now, to overcome the molecular replacement, single isomorphous replacement was proposed. But here, for an unambiguous determination of phase, one needs at least two derivatives. And the second derivative, the heavy atom, should not occupy the site occupied by the first heavy atom, which is not under the control of the experimentalist. When you say heavy atom, I mean atom with the larger atomic number like mercury, uranium, gold, and so on. You take the native protein and soak it in a heavy atom salt solution. As you know, 50 to 60% of the protein is occupied by solvent molecules. Therefore, these heavy atoms will replace some of the water molecules and sit inside the protein. So this is known as the derivative. So we should have at least two derivatives in this single isomorphous replacement to have unambiguous phase value, which is termed as a multiple isomorphous replacement. And another thing is, whatever derivatives you make, 2 or 3, all of them have to be completely isomorphous. What do you mean isomorphous? Isomorphous mean original protein has some, it has crystallized in some space group with some unit cell dimension. After soaking it in the heavy atom salt solution and after forming the derivative, we have a new crystal. So that cell parameter and the original cell parameter should not change more than, it is a 0.1% or 0.05%. When will the cell dimension change for the derivative? Unless the heavy atom it is occupying at the site made substantial changes in the conformation so that the unit cell was unable to occupy this molecule, the unit cell cannot be expanding. Which means that if it has expanded, let us say unit cell differed between the native protein and the derivative by for 2% or 3%, which means that it is no longer the same protein. Size has increased due to so many conformal changes have been happening. That is the reason why they have been very specific about multiple isomorphous replacement. Whatever derivatives you make, all these derivatives, their cell dimension should not deviate much from the original parent molecule. So the deviation should be less than 1% or so. Any change in the cell dimension, as I told you, will eventually mean some other protein about which we are not interested. So because of these failures in each technique or the stringent conditions imposed, like your homologous percentage in MR or this isomorphism in MIR, so number of proteins tackled was very less until we have the development of your synchrotron source in the year 1980. So due to the limitations of this technique MR and MIR, only countable number of proteins were determined for the three-dimensional structure. Even up to 1980, I can say the number of protein structures are very much limited. After the upcoming of this synchrotron sources, only a number of protein structures determined were large. Until 1980, molecular replacement technique and multiple isomorphous replacement were the only two techniques available for tackling the phase problem in macromolecular crystallography. Then came the advent of synchrotron radiation, where the incident wavelength can be tuned even up to the fourth decimal to match the absorption wavelength of the heavy atom present in the protein. In these techniques, data are collected either at a single wavelength where the anomalous scattering of the heavy atom is more pronounced, which is known as SAT technique, single wavelength anomalous diffraction technique, or at three wavelengths, one at peak where F double prime is maximum, one at the inflection point where F prime is the most negative, the minimum, which is used in the multi-wavelength anomalous diffraction technique, and the third data is collected at either left remote or right remote of the curves. The curves denote F prime and F double prime, which we will see later. The heavy atoms are located from by first difference Patterson computed with the peak wavelength data and dispersive difference Patterson computed from the inflection point data and also from the data from one of the remotes respectively. Multi-wavelength anomalous diffraction or MAD data collection is identical with multiple isomorphous replacement data collection techniques with 100% isomorphism because we use the same heavy atom in MAD experiment. It is just a physical substitution of varying the wavelength to make it to behave like another atom, but not a chemical substitution as in MIR. Let us now study these different methods in detail. Let us now discuss something about the molecular replacement method, which was originally proposed to solve a macromolecule. Molecular replacement was a traditional method used in macromolecular crystallography when the structure of a related model was available. The homology should be there, at least 20 to 25% homology is there, means we can use it as a model, put it in the unknown unit cell where we don't know where is the molecule, then you get a trial number of atoms after doing rotation and translation, and this position can be used to obtain phases. Then slowly we can develop the model after doing the Fourier synthesis. For example, human phospholipase A2 structure and snake venom phospholipase A2 structure are more or less structurally homologous. It is more than 98% we have homology. Suppose you have collected your X-ray different data for snake venom PLA2, we can straight away use this model structure available for human phospholipase A2 to put it this way and get the full structure of the snake oil phospholipase A2. No problem at all. Michael Rossmann and his group from Purdue University, USA had made seminal contribution in this topic of molecular replacement, and you can refer to the review for the existing literature up to 1972, and this was compiled by Michael Rossmann in 1972, and it was titled as Molecular Replacement Method, published by Gordon and Brish, New York, USA. And in the molecular replacement method, the first program was released by Merlot by Paula Fitzgerald. At present, an automatic program has come from Dr. Navasa's group. Of course, Navasa himself has written it initially. Now we have added so many things. And this is from France. His program name is AMORE, Automatic Molecular Replacement. This is widely used and this is fully automatic. All these programs are available in the free domain, CCP4, Collaborative Computational Project number 4. Anybody can use it. Another program name is MolRep, which has many macromolecular program suits as in CCP4. This is also one among the program for doing a molecular replacement. Let us consider a structure of two identical units in different orientations. If one does a Patterson function for the structure, three types of Patterson vectors can now be found, namely 1. The self-Patterson vectors of one unit, 2. The set of self-Patterson vectors of the other unit, and 3. The cross-Patterson vectors formed between the two units. So for example, let us take a structure containing 4 atoms. So what do you mean by self-Patterson? Patterson is an interatomic vector. Therefore, interatomic vectors of self-Patterson will be R11, R22, R33, R44. Then what are the other interatomic vectors? If you consider 4 atoms, 1, 2, 3, 4, then the interatomic vectors are R12, R13, R14, R21, R31, R41, R23, R24, R32, R42, R34, R43. There are 12 cross terms available, then 4 self. So totally 16 terms are there. This is what we mean by n square peaks. But usually in a Patterson, peaks to be analyzed is n times n minus 1 or n square minus n. That is 16 minus 4. 4 is subtracted from the 16 because this 4 is self-Patterson peaks. So we have to analyze 12 peaks only. Only problem is, it's a simplified case. We consider 50 atoms, 100 atoms, the complication is more. Two self-Patterson vectors will be related by a rotation as these are in different orientations. In the cross-Patterson vectors, some or all will be outside the volume extending from the origin by the overall dimensions. But the self-Patterson vectors of the two units will all be within this volume. Now, the superposition of these Pattersons will show similar way. The superposition of the molecular self-Patterson derived from different crystal forms can provide the relative orientation of the two crystals when the molecules are aligned. Rossmann and Blow in the year 1962 used a rotation function R of theta 1, theta 2, theta 3 defined as R of theta 1, theta 2, theta 3 equals integral over u p1 of x times p2 of y times dx. This is equation 18.1. Here, P1 of x denotes the value of the Patterson at x for crystal H, and P2 of y denotes the value of the Patterson at y for crystal little p. And theta 1, theta 2 and theta 3 are the three angles which rotate the Patterson P2 from its initial arbitrary position, and the integral is over the volume capital U of the sphere centered on the Patterson origin. The best combination of theta 1, theta 2 and theta 3 is the one which has maximum for the right hand side of the above equation 18.1. A molecular replacement involves two functions. One is a rotation function, another is a translation function. Why you need this? Because as you know, you want to determine a molecule in a particular unit cell for which you are taking a homologous structure, but that structure was lying in another unit cell, okay, in another orientation. So we cannot take the same molecule and put it here. Okay, you can put it, but after putting in the unknown unit cell, you have to orient it to proper rotation and proper translation to match with the data. That is known as, from the known intensities, we can do a Patterson, and using this procedure, it's a complicated procedure. Using this Patterson only, we are getting the positions of the correct atoms here. Of course, you have to model it from the known structure. So, translation part is there, rotation part is there. In space group, other than the P1 tricyclic space group, the origin of the unit cell cannot be chosen arbitrarily. Usually, for the sake of convenience, our origin will be taken only on the symmetry axis. If the screw axes intersect, we take as a customary as the origin at the intersection point. In these cases, whenever an exactly oriented reference molecule is translated in the unknown unit cell from the known unit cell, the symmetry related molecules also move accordingly, and all the intermolecular vectors will change in the unknown unit cell. It is only when all the molecules in the crystal cell are the correct position, the Patterson cross vectors superpose onto those of the observed pattern. This is the technique used in molecular replacement, cross Pattersons. During the translation functions, in the Patterson superposition, it will be very noisy and with many small maxima. In the literature, many translation functions have been proposed. Gosser and Blow proposed a better translation function. The set of cross vectors of the calculated Patterson from one molecule to the second molecule can be written as P12 of U, which is equal to integral over the volume rho 1 of x times rho 2 of x plus u times dx, which we call it as equation 18.2, where the rho 1 and rho 2 represent the electron densities of two molecules. If the molecule 1 is now translated, a new vector will define its origin, but at the same time, molecule 2 will enter the cell, and for every value of the shift S1, a new function P12 has to be calculated. In translation functions, the intermolecular vectors are of importance, and hence translation is considered as a function of vector little t equals S2 minus S1 defined as a local origin with respect to a symmetry element. If P observed of U is the value of the observed Patterson at U, the translation function capital T of small t is defined as T of t equals integral over V P observed of U times P12 of U comma t times du. Now, only when the two Pattersons superpose, the t will be maximum as given in 18.3, and little t is adjusted for obtaining maximum value of capital T. So this is the best translation to be applied to the best oriented molecule to have the best start for phasing using molecular replacement technique. Nowadays, the things are different. For doing molecular replacement, you just have to identify the protein data bank entry which is homologous to your sequence, then feed those coordinates, then automatically you will be getting a new coordinates where the rotation matrices and translation matrices have been applied to the original data, homologous data, and this with the new coordinates you have to just proceed with electron density calculation. Now we are going to cover two important topics: single isomorphous replacement, denoted or abbreviated as SIR, and multiple isomorphous replacement, abbreviated as MIR. By measuring the intensities of Bragg reflection from a native protein crystal, one knows the magnitude of the structure factors mod Fp alone from the measured intensities. But the phases can take any value from 0 to 2 pi. So this will be shown in the next figure. To overcome this ambiguity of phases which can take anywhere from 0 to 2 pi, we are going to add a heavy atom. This is done by soaking the protein crystal in heavy atom salt solutions of heavy elements. When I say heavy element, the abbreviation is capital H. These heavy elements may be that of gold, Au, platinum, gadolinium, samarium, etc. Then one crystallizes derivative, that is protein plus heavy atom, symbolically we call it as capital PH, where a heavy atom contribution to the structure factor mod FH is added to mod Fp, the protein structure, to get the structure factor of the derivative mod FPH. Here we see the figure representing the modulus of Fp, the structure factor amplitude of the native protein, which is known after collecting the intensity of the native protein crystal. Here if you just see, in the circle, the radius is same all over, no, everywhere. Therefore, alpha p can take any value from 0 to 2 pi. So this is the Argon diagram. So we are going to show this as a Harker circles later. Since you know we have crystallized the derivative, we can collect data for it. So intensity of this pH is now available, which is equal to square of the structure factor amplitude of the derivative, square of mod FPH. Now, mod FPH is square root of IPH, which is to be equal to modulus of Fp plus FH, because we get the derivative structure factor by adding the heavy atom contribution structure factor to the native protein structure factor, which means Fp plus FH equals FPH, or FH equals FPH minus Fp. This means that by doing a Patterson with FPH minus Fp as coefficient, we can get the position of the heavy atom from the Patterson. But there are two possible solutions to this equation, because we are getting an alpha from the formula, cos alpha prime from the formula, cos alpha prime equals mod FPH square minus mod Fp square minus mod FH square divided by twice mod Fp mod Fh. Because it is cos alpha prime, for both plus and minus alpha prime the value will be same. So this is equation 18.5. Now by adding a derivative, by adding a known vector Fh to Fp, the phase range for alpha p has come down from 0 to 2 pi, or to just two values, alpha h plus alpha prime or alpha h minus alpha prime. Now we have, instead of 0 to 2 pi ambiguity, we have only a twofold ambiguity. Alpha prime is known, alpha h is also known. Now the question is, the value is either alpha h plus alpha prime or alpha h minus alpha prime. So we will show it, this is the Argon diagram, the next projection. So now we have twofold ambiguity. In the theory of such single isomorphic replacement, Rasman and Karta and Pathasarathi have made substantial contribution. Again, Karta did his research associate under Professor G. N. Ramachandran. Professor R. Pathasarathi was Professor G. N. Ramachandran's student. He later on moved to Rasper Park Cancer Institute at Buffalo, New York, where he had his second PhD degree under Professor David Harker. So there only he started the Karta and Pathasarathi together. They had a major role in the crystallography department, and they started publishing many papers on MIR and so on. For the multiple isomorphic replacement technique, Harker in the year 1956 developed the geometrical proof, and Karta and Pathasarathi have worked out the formula. By choosing the two isomorphic derivatives, the heavy atom H1 and H2, not substituting at the same positions, David Harker, using the geometrical construction, which are known as Harker circles, which is shown in figure 18.1, overcame the above twofold ambiguity. The three circles with radii will cut at a single point only. So let us see in the next projection what we mean by these Harker circles. We have earlier seen a circle with mod Fp as radius. Alpha p is the angle subtended by mod Fp with the real axis. Now since the circle radius can be everywhere, it's the same radius mod Fp. Therefore, alpha p has the ambiguity 0 to 2 pi. Okay. Now alpha p is going to have only two ambiguities we have seen. Alpha h alpha prime plus alpha h minus alpha prime. So if we look into the first diagram in figure 18.1, we have mod Fp, the right hand side, added with mod Fh to get you mod Fph, which is the radius of the bigger circle. Mod Fp is the radius of the smaller circle. Then there is another possibility in the left hand side, your alpha p is going, mod Fp circle is there, plus mod Fh is there, then we have mod Fph. Now this is ambiguity, two ambiguities are there, alpha p this way or the other way. To overcome that, we are going to have the three circle construction. So you have to just look at the diagram carefully. Let us have a circle centered with O, and with mod Fp as the radius, draw the circle. So now, next, you have the first heavy atom position determined. You know what is the contribution of the heavy atom to the structure factor. Then with a shift of minus FH1 from O, now we have minus FH1. This is adding with the derivative FPH1. So with the new center shifted from O by an amount minus FH1, now the new center is O1. With O1 as the center, with mod FPH as the radius, you draw another circle. Now these two circles will cut at two different points. Again, ambiguity is there. To overcome that, you choose a third derivative and let it be the heavy atom H2. Then you get the position, calculate the contribution to the structure factor. Then that minus H2, minus FH2 is there. That from O, you shift to the new origin by this amount. Then we have FPH2 from O2. Now with O2 as the center and FPH2 as the radius, draw another circle. So this is a small circle. Now we just see all the three circles will cut at least only at a single point. So using this, we can get the unique value for the phase angles. So this is the procedure, graphical means suggested by Professor David Harker. This is known as Harker construction and Harker circles. From the above Harker circles, we can solve the phase ambiguity when two derivatives were used. The Fourier map with coefficient mod FPH1 minus mod FPH2 square was proposed by Rossmann in the year 1960. This coefficient is square of mod FPH1 minus mod FPH2, which are the structure factors obtainable from the intensity of the first derivative crystal and the second derivative crystal by taking the square root. Now, with this mod FPH1 minus mod FPH2, you subtract and add mod FP. So that's what we have done in the next equation. Now, if you look at the first term, it is mod FPH1 minus mod FP. This is known as isomorphous difference because first is FPH derivative 1 minus native. So this is nothing but isomorphous difference. Delta mod f of iso 1 then minus delta mod f of iso 2, the whole square. Now this can again be simplified as delta of mod iso 1 whole square plus delta of mod f iso 2 whole square minus twice delta of mod f iso 1 times delta of mod f iso 2. This is given by equation 18.6. So this right hand side term in 18.6 is known as the correlation function of the product of two Fourier coefficients. Anomalous scattering. This is an interesting and important topic one should know in X-ray crystallography. Due to the possibility of selenium-methionine derivatization of protein molecule during the expression itself, selenium atoms can be introduced wherever sulfur atoms are there. Sulfur atoms, as we know, they are there in the methionine residues. So automatically the methionine residue after being introduced with selenium atom is called seleno-methionine, Se-Met. In all the synchrotron centers, one beam line is already tuned to the selenium absorption frequency. Data can be collected at the tuned wavelength where, due to the anomalous scattering effect, substantial number of Bragg reflections which differ in their intensities IHKL and IH bar, K bar, L bar for the inverse reflections could be measured very accurately. And now anomalous difference Patterson map can be calculated where the coefficient will be square of the mod FH minus mod FH bar. Earlier to the development of sensitive detectors, macromolecular crystallographers used to collect synchrotron data at three wavelengths. Let us see the figure to have a clear understanding. At a wavelength lambda 1, closer to the absorption frequency called the peak wavelength, the intensities of HKL and H bar, K bar, L bar reflection will differ a lot, and at this point F double prime is the largest, the imaginary but correction is the largest. You can see it from the graph. Second, the measurement of data at lambda 2 at the inflection point where F prime is the least, most negative value. And third, measurement of data at two wavelengths lambda 3 and lambda 4, the left and right remote respectively. Now, from the module on anomalous scattering, we know that The atomic scattering factor F equals F naught plus F prime plus I F double prime, which is called the equation 18.7, and modulus of this little f is nothing but square root of F naught plus F prime whole square plus F double prime square. Any change in F prime, usually negative, will alter the real part of the anomalous scattering term and is equivalent to the substitution of one heavy atom in place of another, because the atomic number differ and hence F will differ. So this multivalent anomalous diffraction technique is identically equal to multiple isomorph replacement technique with 100% isomorphism. The MIR technique is a chemical substitution, whereas MAD is a physical substitution. Here we have two figures. The first figure tells you what are all the wavelengths possible in the curve, lambda 1, lambda 2, lambda 3, lambda 4, which we have discussed previously. Then it also shows other figure 18.2, where the variation of F prime and F double prime corrections near the absorption edge are detailed. There is a sharp increase when the incident wavelength or frequency goes to the absorption edge. So this can be seen in the F double prime curve, where F double prime becomes maximum value in the positive. Near to that, if you just see, F prime curve has a dip at this wavelength, and the energies are marked in the x-axis. The wavelength is marked again in the upper portion. Atomic scattering factor values for the F double prime and F prime are also marked here. Below 0, these are all negative. You clearly see that whenever you have the data collected in the remote wavelength, left or right, so these F prime values are about -2 or so. Whereas if you collect at inflection point where the dip is there, it will be close to -8. So a difference of 6 electron is possible when you shift from the remote to the inflection point. So now this change is due to the change in real part. This is due to the F prime changes. So this means that an atom is there. It is made to behave like another atom, which differ in atomic number from the previous atom by 6. So eventually, since the real part is changing, the such factor amplitude collected at these two wavelengths for the same reflection will differ. So by measuring the intensity differences between the same sector factor collected at these two wavelengths, a Patterson can be calculated. That is 1. This is known as dispersive difference Patterson. So from the upper thing, if you just see that F double prime is the maximum, the consequence of this anomalous scattering is the violation of Fresnel's law. Therefore, we have hundreds of reflections at this wavelength, which will differ between I of HKL and I of minus H minus K minus L. This is the Bifer difference. So now you can take for the same wavelength mod FHKL minus mod F H bar K bar L bar as the coefficient of the pattern synthesis. This also will give the position of the heavy atom. You can cross check the position from the two Pattersons. Originally, since the detectors were not so sensitive, people used to do both MAD and SAD experiments. But nowadays, even difference of 0.05 in the intensities between HK and H bar, K bar, L bar reflection can be measured efficiently. Therefore, it is just SAD technique which is being used now. It also saves the data collection time by 2/3. And all these things, the synchrotron source is already tuned to the selenium edge absorption. Therefore, doing the molecular biology experiment, you do the selenium-methionine derivatization. The sulfur in the methionine is derivatized as a selenium. So suppose you have 5 methionines there in the protein. So during derivatization, 5 seleniums will be there. You make the crystal. Actual seleniums are there. Then when you collect the K-edge absorption for the selenium in the synchrotron, automatically the selenium position can be picked up. That can be used as a starting phase. Then rest of the phasing can be computed in the electron density calculation. As explained now, for the same Bragg reflection, the intensity collected at the inflection point under the left or right remote will differ because the enormous change is there in the F prime value. Therefore, structure factor change will be there. So this difference due to change in intensities or structure factor magnitudes mod F of H same reflection at lambda I minus mod F of H lambda R. Lambda I means inflection wavelength, lambda R means your remote wavelength. So this is known as dispersive difference. So since you are doing a Patterson, a square of this is used there. The Patterson with the square of this as a coefficient of the Patterson is known as dispersive difference Patterson. As explained just now, the detectors were of inferior quality. To measure even the small differences, we used both the techniques to obtain the heavy atom position, but now the detectors are so sensitive, so people have jumped to SAT technique. As an example to inspire you, I am just showing you the real data we have collected with selenium absorption edge. The selenium peak wavelength is 0.9788. There are 3 blocks of data. First block shows peak, second block shows edge, third shows remote. Edge means inflection. Now, at the peak means we talk about I plus I minus. I plus means intensity of HKL reflection. I minus means intensity of minus H minus K minus L reflection. If you just see the data collected at the peak, that is where FW prime is the maximum, that is lambda 1, where intensity of HKL is not equal to intensity of H bar, K bar, L bar, and hence modulus FHKL is not equal to modulus F H bar, K bar, L bar. You can easily see this violation of Friedel's law here. You take 14 deflection. For HKL, intensity of HKL it is 3343, whereas for intensity of H bar, K bar, L bar it is 3135. Roughly they differ by 200 units. So like that, hundreds of reflections will be there. Therefore, when you use absolute of this mod FHKL at lambda 1 minus mod F H bar, K bar, L bar at lambda 1 as a coefficient of the Patterson. So this coefficient when used in the Patterson is known as bifold difference Patterson or anomalous difference Patterson. This will eventually give the position of the heavy atom because hundreds of reflections are there which will differ at the intensities. So this is the first one. So now again if you look at the edge inflection point, here you don't find much variation between intensity of HKL reflection and minus H minus K minus L reflection. Let us consider the reflection 1114 from the second block. The intensity of HKL is 2664 roughly, and intensity of minus H minus K minus L is 2657. So in this case we merge them together, let us say roughly is 2660. But same reflection 114, when you take it to the remote wavelength, it is 3196 for HKL reflection and 3233 for H bar, K bar, L bar reflection. So, more or less, this is 3000 average, approximately 3200 here, that is 2660. So, between the edge wavelength and remote wavelength, due to change in the real part, we have enormous difference in the intensities. Therefore, such a factor also will be differing. So, now you do a Patterson with the coefficient mod of FHKL at lambda inflection I minus mod of same reflection F of HKL at remote. So this will also reveal the position of the heavy atom for cross-checking. So students, let us summarize what we have learned so far in this module. The missing information of the phase values of Bragg reflections from the diffraction experiments which is required to perform a Fourier synthesis of electron density to locate the electron density maxima or the atomic sites is a bottleneck problem in crystallography known as phase problem. We have seen that different methods like molecular replacement, single isomorphous replacement, multiple isomorphous replacement, and anomalous scattering methods could be used to obtain the phases. The process of searching of an unknown structure using a homologous structure is called MR or the molecular replacement, which requires at least a similarity of 25% between the structures considered. Heavy atom derivatives were used to overcome the limitation of molecular replacement to obtain phase in which crystals are soaked in heavy atom salt solutions at controlled experimental conditions without changing the unit cell and conformations. The difficulty of preparing a second heavy atom derivative for MIR has led to the technique known as multi-wavelength anomaly diffraction MAD or single wavelength anomaly diffraction SAD, where data are collected either at 3 different wavelengths or at the peak wavelength where the FW prime is largest, and the heavy atoms were liquidated from the bifold difference Patterson in case of SAD, or from dispersive difference Patterson and bifold difference Patterson in case of MAD experiment. Due to this technology only, nowadays per week at least 125 to 150 structures are newly deposited in the protein data bank. Thank you.